Hello. Hey, folks. I'd like to welcome Martin Durant, staff software engineer at Anaconda with his talk, Akimbo Vectorized Processing of Nested Ragged Data Frame Columns. Thanks for being a part of the conference, and I'll let you take it from here.
Thank you very much. With a slightly updated, better sounding subtitle, when your data doesn't fit in your data frame, which is what this logo is about. Here's your data frame in the middle, and here's your arms coming out the side, which is why this is called Akimbo. Okay, I'm still pretty old school, so I have an outline. Got to go over where this has come from, demo the features, talk about issues and where we go from here. And I'll try and leave some time at the end for questions. Okay, so if you are at PyData, I think you know about data frames, but let's go over why we use them just a little bit. So tabular data has been around for a long time. Basically, a table is a group of one-dimensional arrays. We call them columns. Each one has a particular homogeneous data type. And since the introduction of SQL back in the 70s or something like that, tables have been around and have been used for data analysis all over the place. In Python, we usually call them data frames, and this came in with pandas many years ago. There are other data frame libraries around, and they have the same kind of table structure. And the reason we use them is that we get fast vectorized processing of the data that's in them. Using NumPy or whatever compiled kernels. And we have access to the many SQL-like functionality in Python, which is nice if you want to program in Python and not SQL. Now, in the past few years, something has happened in the Python data frame ecosystem and a broader tabular ecosystem, and that's something called Arrow. And whereas in the past, if you had deep nested data, we'll get onto what that means in a moment. In Python, you would have to iterate over the various dictionaries and lists and things. Arrow is a data model that includes both tabular, so data frames as you normally think of them, and nested variable length things. So this originally came out of Parquet, or at least Parquet was the first widely available file format that supported this kind of data. Not only does it have one-dimensional arrays, but you can have missing data, variable length, nested records within records. And I'm going to refer to this kind of thing as JSON-like data. Now, Python can work with this fine, but not vectorized. It's usually iterative and slow. So Arrow has come along, and it gives us a way to represent this data in memory. Basically, it implements the full generality of JSON-like data, so long as you have a consistent schema from one record to the next. Since Parquet, there are other ways to store this kind of data. I'm not going to get into them, but it's become general that new binary column-oriented data formats support Arrow, so we can load it and represent this data in memory. That's nice. It's also the backend for most, maybe all of the data frame libraries that are around now. So we only really need to support one thing to be able to support tables in general and the JSON-like nested data in particular. Okay, so where does Akimbo fit in? Well, first I'll mention a thing called awkward array, AK for short, which is where the AK in Akimbo comes from, which is an API. It's a library and an API over nested variable length data structures. It originally was built for analyzing physics data, but it's vectorized and fast, and it works with this deeply structured data, and I'll show you in a moment. It also works on GPUs and CPUs, and it integrates with Number, which is great for Python usage. Akimbo brings these two things together. It brings a NumPy-like API from Awkward into the data frame world so that you can use it alongside your pandas or polars or whatever it is that you use for your day-to-day work. So the current integrations are with pandas, polars, DAS data frame, and cuDF. Basically, what happens is that your data frame gets a .ak accessor, and you can use this to apply a NumPy-like API to your data frame complex data column. You can apply numpy-ufuncs and aggregations on any level within your schema tree. You can do string and date time operations. You can run number, as I mentioned, under GPU and CPU, and you can attach object-like behaviors. And we won't have time to demonstrate all of these, but here's just a couple of things. This is not code. I'll show you the notebook in a moment. So let's say this is pandas example here. You have a series, which is a list of lists. If you just wanted to add one to every element of these internal lists, you can't do it using standard pandas syntax. But as soon as you do .ak, you can. You can do .ak plus one, and that will add one to every one of the elements of the list of lists and maintain the same structure. And you can do aggregations like max of each list, and you can apply general functions to it. Okay, so for those that find this vaguely interesting, I'll show resources at the end, but there is a certain amount of documentation about this. Akimbo is new. We want feedback. We want people to try it. So I'm hoping that people will go to the various sources of documentation and try out the examples. In particular, the example that I won't go over is the second one here, this high energy physics, HEP, walkthrough, in which we're going, it talks about particles. And I realize that there are many scientists at PyData. This is not SciPy, but still. These particular data sets used by the high energy physicists are very complicated. And the particular slice of the data set used for the example are these particles, where each particle has various properties and causes a cascade of subparticles, a variable number of those, and each of them also have properties. If you want to aggregate a result over all of your science data, it's really hard to do that either with just arrays or with just data frames. So you use Awkward to do it. And if you use Akimbo, then you can use both Awkward's API and dataframe API together. Okay, so that was quite a few words. I'll catch my breath. And we can go on to the first of our demos, which is basic usage. So here we have this example running inside Jupyter. This is going to run on Anaconda's repo data, one of the repo data JSON downloads. Anybody who uses Conda, you actually use this in the background, maybe without knowing it. But I've downloaded a repo data JSON file, which is a single massive JSON object. And in a small script, which I don't have time to show you, I do some processing on it to take out most of the data, some small simplifications, and save it to Parquet. Again, Parquet is a format that allows for variable length and nested data, and it has internal compression. So in general, compared to text formats, you will always save a much smaller file. It's true that this original JSON can be compressed to a similar factor, but Parquet has advantages enabling you to load it much faster and to only load some of the columns if you want to. So let's have a look at it. Again, this is using pandas, but you notice up here I also imported akimbo.pandas. First of all, here's the pandas data frame. It has lots of columns. It has lots of data. Some of these columns in particular, we'll look at this in a moment, are quite complex. You can look at the various types here. This is using the arrow backend, by the way, which is still optional in pandas, but it is becoming more dominant, and I believe it will be the only option, or at least a default option at some time in the future. You can see there are some complex types in here. These are complex arrow types. Let's look at a simple column, license family, which is just strings. You can do normal data frame type things to these, such as let's look at what different types of licenses there are across all of these different packages in the repo data. Most of them apparently are BSD. Okay, we could use this to filter, group by, whatever you like. Let's look at one of the more complicated columns. This is the CLI options to Conda when building, I believe. These are, each element is a list. Within that list, we have a dictionary, and the dictionary has keys and arguments, values, which are all strings in this case. And this is the first row. This is the second row. It's interesting, but it's not obvious what to do with this, and it's only one level deep. A more interesting field in this data is the dependencies. Every package has a bunch of dependencies. You shouldn't be surprised. These are conda packages. They depend on things. I don't know off the top of my head, I haven't shown it here what the first package is, but these are all the things that it depends on. And you can see some of these, it depends on JupyterLab, but it has no further information. So it just said it needs JupyterLab of any given version. But some of them have specifics. So it requires Python. It needs to be greater than or equal to this particular version of Python. These are integers. So we can do fast vectorized processing on these integers in here. Okay, let's do an interesting computation to this data. I'm going to ask for cases in which the dependency is called NumPy, exactly, and the first element of the required version is 2. And most of you may be aware that NumPy 2 came out in the summer. It was a big deal. All of the resources are in the repo that is linked in the resources tab. So I'm going to require NumPy, and the first element of the versions list is equal to 2, and I'm going to see if any of, you see this is a single row and it has many dependencies. If any of the dependencies matches this requirement, then I'm going to count them. Now, I could have used this to filter to do more information, find more information on those particular packages, but in this case, I'm just going to add up all the cases where it's true. And this gives me, I'm also timing it. This gives me, there are 385 packages in this complete data set, of which there were 42,000 packages in here. And of those, 385 specifically mentioned a requirement on NumPy version 2 point something. And this is how I did it. I formed a discriminant function, and I used this to apply using the .ak. This would not have worked without the .ak. This is a way to bring this again into the data frame format. We can look at one of these, and if you look here, you can see that this indeed requires NumPy to be less than 2. Presumably, it was not yet built to work with NumPy 2. This is a single row. You can see complex data here. There are other ways I could have done the same compute. So here's a function. This is an iterative approach. I start off with 0. I'm going to go through each of my packages. For each package, I'm going to go through each of the dependencies. If the dependency has the name NumPy and it has a version specified, and the first of those versions is equal to 2, I'm going to add 1 to my counts. So there's the definition of my function. First, I'm going to just do this on the pandas data frame. You can see I get the same answer as before. But interestingly, I can also numberjit this function and run it. And for this, I have to use the akimbo accessor, otherwise it won't know what to do with this data. This is a way of bringing number into the fold. I get the same answer. And the interesting thing is that if I do this, wait a moment for the timing to happen, you will see the iterative approach using Python is a factor of what, 40, something like that, times slower than using number, which we can only do because of Akimbo. Okay, so Akimbo allows us to vectorize our kernel very efficiently. That's good, but maybe there's another way to do this using pandas, using explode. Explode takes each nested thing and makes a new row for it. So we can explode the depends column. This actually takes a few seconds to happen because it's an iterative process to do that. It's iterating over the internal dictionary there. And we can then explode the versions list because we're only interested in the first version. I could have written a way to do this iteration and just select the things that I needed immediately, but this is what you end up doing. Here is my expanded data frame. This now has a lot of rows, and not surprisingly, the memory use of this is much, much bigger than it was before. But I can still do the same compute, and now I get it's about as fast as the original Akimbo, but it's a bit slower than Number was. And I can see here are my versions counts. Okay, so that was an example. And we'll have more examples in a moment, but let's just recap the features of what is being shown here. Akimbo brings you a NumPy-like API. You can do slicing, you can do filtering, you can use ufuncs, you can use operator overloading like the plus, you can use broadcasting in the NumPy sense to be able to, for example, add a single number to a whole bunch of other numbers. You can apply and transform your deeply nested schema structure. You can use number, you can do that on CPU and GPU. You have access to string functions and datetime functions and other pluggable sub-accessors. And you can apply specific object-like behaviors. For example, if you know that a particular part of your schema tree is not just numbers, but it's a vector, and you want specific behaviors that are inherent to vectors, you can do that. I don't have time to show all of those things today, unfortunately, but I'll show you a couple of things yet. And also, it's exactly the same usage whether you're using pandas or polars or DAS data frame or cuDF. cuDF is the NVIDIA Rapids GPU implementation of the pandas API. There are some caveats here. The polars usage is eager. The DAS data frame usage is not global aggregations. You can do aggregations only within partitions, but that gets you quite a long way. And finally, I am working on and have some experimental code for integrating with Daft and with PySpark, which are other distributed data frames that you might be interested in. PySpark works on Spark, of course, and Daft works on Ray. Okay, so we're going to move on to the second demo. And here I have actually 4 notebooks, and they are for the 4 different backends. So here again is pandas. Pandas always comes first. It's the most common data frame library. Even those that love polars or whatever will recognize that people usually learn pandas first. Here's a smaller data set. This is an interesting data set because it is generated from HDFS server logs. Again, the script to create this data frame, this Parquet data set from the text input, that can be found in the resources, which is linked in the resources tab, and there's a repo with everything there. You see there's quite a lot of rows here, but it doesn't have that many columns. This is a subset of the total data in this data set, just to demonstrate what you can do with it. We have, in each case, a path to some file in HDFS, a timestamp, and the deeply nested array in which we have a set of blocks. And for each block, we have the IPs at which that block was stored within the cluster. This is the structure of that data. We have strings, we have date times, and we have blocks, which is optional, so it could just be none. And we have a variable length list, including IP and the time at which it was written. The IP itself is a list of IP addresses. So it's fairly deeply nested. We can do some simple aggregation here. Like we're going to look at how many blocks do we have per entry in this log file. So we're doing an aggregation here. We're going to select the IPs, which is the inner column here. and we're going to do an aggregation. We're just going to count how many values there are. And this is saying that it's not the number of rows that we want, it's the number of inner IP values that we want. And you can see most of these values are going to be 1, but we can, once we have this value, this set of results, we can do usual data frame things to it again. So here are the value counts. Most files only have 1 block, but lots of files have more. That's something that you might be interested in if you're looking for anomalies, for example. Or if we wanted to know the replication factor, so now we're going to go into the count, not the number of blocks, but the number of IPs for each block to get the typical replication factor. It looks like this. Usually it's 4, sometimes it's 1. I don't actually know how many nodes there were on this cluster. And we can do this compute, and it's vectorized, it's fast, so we can time it. But interestingly, here's a chain of .ak commands. Each time you do a .ak something, you get back a new pandas series. So you might choose to do apply. This is the same chain of things in here, but it's directly calling awkward rather than going through .ak each time, .ak. It's doing it in one step. And this will be a little bit faster because you're not having to regenerate the pandas index every time. Having done that, I can again do, this is the simplest thing that you might want to do to a set of data frame values, which is most of these blocks have replication 4, sometimes it's 1. As an added little bonus just here at the end, I'm not going to dwell on this. I have a separate package just to show that you can have sub-accessors. So here's my series, .ak brings me the Akimbo API.ip is a specialized API for IP addresses. I can ask for each of these different IPs, which are length 4 byte strings. That's an IP4 address. Is it global? Actually, nothing happens here because I have to, these are all variable length byte strings. I have to first make them fixed length byte strings. And then it looks the same, but now the type has gone to bytes 4. Now I can call IP functions on them. Wherever it finds these exactly length 4 byte strings, it's going to apply, is this a global IP address or not? For each of the replication factors, we see none of them. This is all an internal network. Or I can turn them back into IP strings. So that's all interesting. If you have IP addresses, you might want to do those things. But what I want to show is that these notebooks, I don't have time now to run them all. In polars, this looks the same, except I don't need to specify that it's arrow-backed because polars is always arrow-backed. Some of the data frame API is a bit different, but the .ak API, the Akimbo part of this is always exactly the same. Here it is with Dask data frames. Again, I need this, and now I need .compute if I want to get some actual values out. Those that understand how Dask works will realize that you have to do that. And finally, for QDF, I'm not going to have time to run this either, but this looks again exactly the same. QDF isn't based on Arrow, but it's based on something that's very much like Arrow, so everything still works. And we get, if you run this yourself, if you happen to have a NVIDIA GPU, you get exactly the same answers. Okay, so where do you get your data from? I mentioned Parquet. There are other binary columnar data files out there that support this kind of thing. Actually, lots of them these days. You might get it from text. I mentioned log files. I mentioned JSON. There are others, XML, whatever. Lots of structured ways to give deeply nested text. There are record-oriented binary files like Arrow, message pack, maybe not so common these days, but you might have that. Most interesting one here is database joins. If you have 2 tables in a one-to-many relationship, that actually is a nested variable length thing, just exactly the same as you have here. So Akimbo can be your way of expressing ORM that you might be used to from Django or whatever you use for that kind of thing, plus lots of other places that you have this kind of data, but Python typically has not been used. But I want to know what kind of data people here have, and please, feedback is what we're after here, really, and especially anything that has interesting behaviors like vectors I mentioned, geometry, IPs I mentioned. There's lots of things where the units, the variable length structures might have specific things that you want to be able to do to them. Okay, these are discussion points. I'm going to just mention the first one really. SQL can do a lot, but Python is much easier. Sometimes you can do some of these things in SQL if your data happens to be in a database already, or maybe you can do them in DuckDB if you have your data in various files. But SQL is hard and you can't express all kinds of algorithms in SQL. So if you have a complex algorithm and you have enough data that iteration and explode don't work, that's when you need akimbo. There are questions about lazy, so I can answer those. Just to mention our plans, we want more backends, more types, more examples, and your feedback, which is why I'm here. All right, that's it. Those are the resources, and I can check through the couple of questions that are here and see if I can answer them in the time left. Does Akimbo only work with Arrow? Yes, Akimbo is implicitly using Arrow under the hood to pass data to and from the data frame. If your data is in pandas and not in Arrow, it will be converted to Arrow as the first step. How does pandas know? Pandas supports a way to register accessors. So this is an official API. For some of the backends, there is not an official way to register your API. So we use some Python magic to do it, but the .ak will be there and it will work. Okay, thank you, Reg person. That was in the other talks too. If you have pandas and you load a deeply nested thing, then if the D type is arrow, you will get nested arrow structures, which is what we would prefer. If your D type backend is NumPy, then you will get Python objects, which are much slower to use and use a lot more memory. So that's not really recommended for this type of data unless you have so little of it that it doesn't matter and you're happy just iterating over it. I don't have any NLP examples. I don't know that much about NLP myself. If you can structure it in this way, where you have variable length lists and structures, and those two things nested within one another, then sure, I'd like to see such an example and what you do with it currently. Please come to the repo. All issues welcome. That's it from me.
Good morning. Thank you so much, Stephen, for your wonderful presentation. And thank you, attendees, for joining us for this wonderful session as well. And I do want to close it out by letting you know if you'd like to continue the discussion, head over to the Discord. The link will be available in the reception area. Also, a recording of this session will be available shortly for rewatching. So for those interested in more casual conversations with Stephen, the lounge is open in the reception for small group discussions.
I
So see
just
you there.
add, I'm not sure who Stephen is. My name is Martin.
Oh, sorry,
And
Martin. So sorry.
yeah, that's fine.
Stephen was here. I'm mistaken it. So sorry for Martin. Thank you. And I will close it now. Take care.